Yes. Good morning, class. Today we are going to discuss the halting problem of Turing machine. In the previous lecture, we have completed the universal Turing machine. So, I want to recap the universal Turing machine today, and then start the halting problem of Turing machine. Right. So, the universal Turing machine is the machine where there are two description of Turing machine can be represented with the help of two tuple, that is M and W, where M is what? M is the machine and W is the string that you have to pass into the machine. So when you pass the W to the universal Turing machine or UTM, then machine will decide whether this is accepted or rejected. Then machine will reach to the halting state. So this is about the universal Turing machine. And now, if we talk about in detail, then universal Turing machine consists of three tapes. Tape one consists the description of the machine. Tape two consists the tape contents, and tape three consists the states of machine M. So these are three tapes that are used in uh, case of the universal Turing machine. Here you can see these are the bidirectional signs. So this is the universal Turing machine, means the finite control. So finite control can write on the tape or can be read from the tape. So this is about the uh, universal Turing machine. And now there are two things. First is the description, and another one is the invention. So in 1936, the universal Turing machine is proposed by in a paper by the Alan Turing, right? And the Turing machine essentially required two things. First is the program, and another is the data set for the program to process. There are two important points here. So a program is simple like a machine, and data set is just like the string. So this diagram is fruitful for us that it require these two essential components. First one is the machine, that is the or the program. Another one is the string, or you can say here it is the data set for the program to process, because a machine will execute the string, then only you can say that the string is accepted or not. So this is all about the universal Turing machine. Now, today I am going to discuss the halting problem of Turing machine. So halting means, as we already know, that halting means terminating. Right after execute the string, our machine will halt. Means machine will terminate. This is the simple problem. This is the simple thing or simple meaning of halting. Right. Another point is it this problem halting problem is unsolvable problem or undecidable problem. Both are the same thing. So what is the meaning of unsolvable problem or undecidable problem? If we have the solution of any problem in the form of yes or no, then we can say this particular problem is decidable or solvable. Is it clear? If we have the if we solve any problem in case of yes, if we give the answer of any problem in the form of yes or no, then we can say that particular problem is decidable and solvable. If we cannot solve any problem, if we are not able to give the answer in the form of yes and no, then this type of problem is called unsolvable problem. So now the important point is the halting problem is decidable or solvable or undecidable or unsolvable. So the point is halting problem is undecidable. You may surprise by uh, listening this thing that halting problem of Turing machine is unsolvable or undecidable. That means, in case of undecidable, as I already told you, that we should give the answer in the form of yes or no. Then this is called the decidable. But here, halting problem is undecidable or unsolvable. That means there is some problem to decide about the halting. They decide about the yes or no. So this is the problem. Halting problem is the undecidable problem. Now we will discuss in detail why halting problem of Turing machine is undecidable. So just in the summary, just we can say that halting problem is what? Suppose we give a program and a input to the program, then determine if the program will eventually stop when it is given that input. Means if we have the certain parameter to decide whether it is accepted or not, and machine will halt. So if this all these parameters are fine, then we can say the problem is decidable or solvable. But in case of Turing machine, just see the problem. So given a Turing machine M and the input string W, and is there any algorithm to decide whether M halt or any input W or not? So in case of the Turing machine, we can't have any algorithm, any procedure that decide whether your machine will halt or machine will not halt. So the now point of communication is machine will not halt. This statement will occur in what situation? आप ये कह सकते हैं. So this is the meaning. इसका मतलब ये कह सकते हो आप कि अगर मैंने कोई डब्ल्यू स्ट्रिंग पास की तो हो सकता है मशीन ने एक्सेप्ट किया और एंड मशीन विल रीच टू द halting state. Another statement is machine उसको execute करती जा रही है for an infinite loop. So in this situation, you can't say whether this W is accepted by the machine or not, because the result of this process will not be displayed. So this type of situation, the situation of infinite loop, is the situation where we can say that we don't have any algorithm whether this is halt or not. So another other point is halting means that the program on certain input, there are lots of definitions about to ensure the halting problem. What is the halting problem? So there is another one is if the program on certain input will accept it and halt, or reject it and halt, and never go to the infinite loop. This is the actual meaning of halting. Means either it should accept the string or it should reject the string, but both the cases our Turing machine should reach to the halting state, right? This is clear. But if your machine is in infinite looping, that means you can't say whether it will accept the string, accept the language, or it will reject the language. So this is actually the problem of halting problem. So we can have an algorithm then that will tell that the given program will halt or not. So in this situation, we don't have any program, algorithm, or procedure that can reflect you, that can tell you that given program will halt or not, or for executing a particular program your Turing machine will halt or not. So in terms of Turing machine, will it terminate when run on some machine with some particular input string? So there is this is the final conclusion, that there is no algorithm and procedure that can determine whether an arbitrary Turing machine will halt on an arbitrary input number. So that's why this problem is called halting problem is called undecidable or unsolvable. So this is all about the halting problem of Turing machine. So if you have any doubt, any confusion, then we can discuss it again. So in case of the universal Turing machine, just we can say that universal Turing machine, there are description in the form of M and W, where M is the machine and W is the string. And W string is processed over the machine, and then machine will decide whether it is accepted or rejected. The same thing can be explained in this format also. In case there are two essentially component, that is the program, you can say, and another one the data set, that data set for the program that you need to process, right? So what is program is simply machine that take the string from the specific format and then execute the code to check whether this string is accepted or not. And it is proposed by Alan Turing in 1936 by the name universal computing machine. And halting means Thus, the meaning, actual meaning of halting is terminating. So the meaning, the descriptive meaning of halting is here, that a program on certain input will accept it, any string, or reject it, but machine should halt, and never your machine will reach to the infinite loop. This is the simple statement that is used for halting purpose. So we can have any algorithm, any procedure that will tell you that the given program or the given string or the given language will halt or not, right? So in terms of Turing machine, will it terminate when run on some machine with some particular input? So there is no algorithm or the procedure that can determine whether an arbitrary Turing machine will halt on an arbitrary input string. So this is the simple statement of the halting problem, right? So now, if I talk about the decidability and undecidability, so simple meaning is, if we have the answer in the form of yes or no for any problem, then we can say that problem is decidable. If we don't have any answer in the form of yes or no, then this type of problem is called undecidable. Or we can say in simplest form that the problems that are not decidable can be undecidable. So this is all about the decidability. What is decidable? This is all about the solvable. This is all about the undecidable and unsolvable, and this is all about the halting problem. So if you have any doubt in halting problem, what is the halting problem, then please let me know. And today I am going to start one more topic, that is the recursively enumerable and recursive languages. So as we know that Turing machine accept type 0 grammar or 0 language. So type 0 grammar is recursive grammar or recursively enumerable grammar, right? And Turing machine is the automation that accept type 0 grammar. So type 0 grammar means all the grammar that we consider are type 0 grammar, means a grammar without any restriction is called type 0 grammar. Clear? So now we will start with the recursive. What is the recursive? And after that, we will discuss the recursive enumerable. There are two things. Just see here, recursive. There are two terms you can say, recursive and recursive enumerable. Right? So what is recursive? A language is called recursive if some Turing machine accept it and halt on any input. Means in case of recursive, it is guarantee that your the Turing machine accept it, and then machine will always halt. This is the simple definition of recursive in terms of the Turing machine. Just you can note down here. This is the important definition, that is recursive. Anyone can ask you what is recursive. Just write in short answer type question. Discuss the definition of the recursive. So a language is recursive. Just this is the important point here. If some Turing machine accept it and halt on any input. Accept in the sense of this, you can say here. Suppose this is the Turing machine. If you pass the input, that is the W, any string to it, just you can draw the diagram also, that will help you to understand the working of recursive. In this case, this machine, M is the machine and W is the string that passed to process a Turing machine. In this case, after the execution, your machine will give you answer. That means what? It may be accepted or it may be rejected. Is it clear? Means what is the meaning of accept? It is the meaning of accept and halt is simply after executing this particular string W, your machine will give the answer in the form of yes or no. Means clearly your machine will produce the answer that this particular string is accepted or this particular string is not accepted. And after that, your machine will reach to the halt state. So this is the simple representation for recursive. In case of recursive, just you can say your machine will give the answer and then it will reach to the halt state for any input. So this type of language is called recursive language. In other words, a language is recursive if there is a membership algorithm for it. Means if we have an algorithm by which we can decide whether it is accepted or rejected, and then your Turing machine will be halt, then we will say that this particular language is called recursive. So you can draw the diagram also. This is very useful in case of explaining the things. Okay. So now another point is, if any language is recursive, then we can say the same thing in mathematical form. If any language L is a recursive language, then M is the Turing machine, then accept it. These are the lines that are taken from the basic definition of recursive. So just we can represent the same thing with the help of the mathematical statement. So just see here, for the string W, if W belongs to L, then M halt is a final state. Means if machine accept W, then it will reach to the final state. And now, if W does not belongs to L, means if any string does not belongs to language, then the machine halt in a non-final state. So that this is the simple example. The same thing can be drawn with the help of the diagram also. Means if this W is passed to the machine, whether it is accepted or rejected, no problem, but there should be clear cut answer. So in this situation, if the machine accept this, or then it should reach to the final state and halt. And another one, if it is rejected, then it should reach to the non-final state. So this is the simple mathematical representation for the recursive languages. So you can note down, this is the basic definition you can say for the recursive languages. Is it clear? So now what about the recursive? A language is called recursive if some Turing machine accept it and halt on any input string. And now another word, we can say a language is recursive if there is a membership algorithm for it. So what is the meaning of membership algorithm here? In case of the membership algorithm, you can find the answer in the form of yes or no. So if you find the answer of any language or any problem in the form of yes or no, then we will say that this is the language of recursive type. And mathematically, we can say if L is any recursive language, that means M should be the Turing machine that will accept it. And for that execution purpose, we can represent the same thing mathematically. Just see here how. For example, W is any string. If W belongs to that language, that means that Turing machine should accept. Right? That means your Turing machine halt in the final state if it accept. Right? If W does not belongs to L, in that situation, your Turing machine should halt and in the non-final state. This is the important point here. Means the important point is, in this case, machine must be halt. In both the cases, your machine must be halt. In the case of acceptance, simply this is the case of accept. So in case of accept, your Turing machine should halt in the final state. So simply, if W does not belongs to L, in this situation, your Turing machine must be halt in the non-final state. Just you can say in both the cases, your machine will halt. So halt means you have the certainty. So this type of problem means we can say that recursive problems are decidable, because in both the cases there is decidability there, or we can say there is a algorithm or procedure by which we can decide whether it is accepted or not, and machine will definitely halt. So this is the simple problem for the recursive language. So is it this definition of recursive language is clear or not? If you have any doubt, then please let me know about the recursive language. Clear? So now, just I want to move towards the remark. So the remark is a problem or language with two answers, yes or no, is decidable. Means if we have the answer of any problem in the form of yes or no, then we can say that type of problem is called decidable or solvable. Right? If a problem or language is undecidable, that means it is not decidable. That means we don't have the solution of that problem in the form of yes or no. For example, if you pass any number or any string to the machine and your machine move to the infinite state, or the your machine move to the infinite looping process, so this type of problem is undecidable, because we can't say whether we will find the solution of that problem or we will not find the solution of that problem. So this type of problem is undecidable. So simply, if anyone asks you the decidable problem or undecidable problem, or solvable problem and unsolvable problem, then you can give the answer by these two statements, that a problem or language with two answer yes or no is called decidable. And if a problem is not if a problem is undecidable, if it is not decidable, obviously. So this is the simple remark regarding these two regarding to the more important point, that is the recursive enumerable languages. So how can we say that particular language is recursively enumerable language, that is RE language, right? So a language is called recursively enumerable if if some Turing machine accept it. So now the point is, by seeing this definition, you may get confused that because this is the similar type of definition. This definition is similar kind of recursive definition, right? A Turing machine is recursive enumerable if some Turing machine accept it. But the main point is this: in case of the recursive, it is definitely decided whether it accept the machine, accept the string, or reject the string, and machine will reach to the halting state. Is it clear? But in case of recursively enumerable, only accepting cases are there. Means it, if W belongs to that particular language, then only it will accept. There, it is not guaranteed that it will provide you the case of rejection. If your machine is in the infinite looping situation, then it is under the category of recursive enumerable. But if you have the clear cut answer of yes and no, and your machine is in a halting state, then this is the situation of recursive. Is it clear? This is the basic difference between recursive and recursive enumerable. So with the help of the diagram, let us see similar to the recursive. So just see here, this is the supposed Turing machine, and this is the W, that is the string passed to the Turing machine. So it may give the answer in the form of accept, maybe in the form of reject, but or plus loop forever. So this is the simple situation in case of recursive enumerable: loop forever, forever. So in case of loop forever, you can't say whether this particular string W is accepted by Turing machine M or not. But in case of the recursive, this is the accept or reject plus halt. Halt is there. So this is the simple difference with the help of the diagram between two definition, that is recursive and recursive enumerable. Now, mathematically, how can we explain the same thing? Let W be a recursively enumerable language and M is the Turing machine that accept it. So for string W, if W belongs to that language, then machine M halt in a final state. This is the same as the recursive, right? There is no difference in this first point if W belongs to L. That means this is the simple case of acceptability, right? Now, another case, the case is the rejection, case for rejection. So in this case, just see here, if W does not belongs to L in this situation, then M halt in a non-final state. This is the simple situation. This is similar as the recursive languages. But another point is or loop forever. So that means in case of the recursive enumerable, you don't have the guarantee that you definitely find the answer in the form of in the form of yes or no. In case of yes, you will find the answer. That's fine. But in case of rejection, it is not guarantee that you will find the answer. So this is the important key point to describe the recursive enumerable. So any one of you have any doubt about the recursive and recursive enumerable, please let me know so that we can explain it again. Recursive and recursive enumerable. I explained the both the things with the help of the diagram, with the help of the mathematical function. Still, if you have any doubt, then please let me know. In case of loop forever, just I'm just explaining recursive enumerable again. In case of recursive enumerable, for example, I this is your machine. Suppose your machine, this one, and I just pass the date of birth, right? DOB, and then your machine will calculate the age and get your machine will reach to the halting state. So this is the simple problem that any machine will always calculate the date after passing the date of birth as a input. Your machine will produce your current age, and machine will get halt. So this is the simple problem of recursive languages. Is it clear? Now, anyone now I pass. There is any machine. In that machine, I pass a number that the value is suppose 2 to the power 5 to the power 5 lakh, suppose. So this is the exponentially value that in this case you are not sure whether you will find the answer or your machine will execute forever. Forever means your machine will execute continuously, but you are not getting the answer, right? So this is the simple of, and this is the simple case of uncertainty, right? You may get the answer, or you may not get the answer. So this is the simple chance of uncertainty, or you can say this is the simple case of recursive enumerable. You may get the answer, it's fine. If it is not the answer, that it may be possible that your machine will move on the infinite looping situation. So this is the simple explanation difference between the recursive and recursive enumerable. Are you getting this point? Now it's clear. Thank you. So this is the all about the recursive and recursive enumerable. This is the main difference between these 2 points, right? Now there are two terms that normally we use in our daily life, that it is very complex, it is not computable, right? So these are two technical terms that we normally use in our research paper, in our writing works. So what is the basic definition of complexity and computability? So just see here, what is complexity? Complexity means a formal measure of how efficient algorithm or program is. Just it refer as the complexity. Means if you compare, if suppose these are the numbers, suppose 5, 9, 2, 3, 1, and now you want to sort these numbers, then in this case, if you use the mechanism by comparing this one, then comparing this one, then comparing this one, then comparing this one, and after the iteration of 10 times, you finalize the list, means you will find the sorted list. Then if you have another algorithm, and after executing 2 times, you just find the sorted list. So first algorithm, it will take 10 steps to sort this order, sorting the order of these numbers, and another algorithm suppose require 2 steps to sorting this algorithm. So on the basis of the time, you can say on that the another algorithm or second one algorithm is better, because two it requires only 2 steps, right? So that means any measurement through which you can identify that which algorithm is efficient. So this is simply called the complexity. This is the simple meaning of the complexity. Another one is the computability. Computability means a formal and intuitive description of computation. Means how can computability means suppose we want to compute any fx equals to x square, right? So that means just we have to compute these value, just you have to pass the input x, then you should reflect the answer in the form of x square. So the basic definition of computability can be described as a formal and intuitive description of computation means just m is the machine and w is the string that passed to that machine. So this is the simple description of the machine. So this is called the computability. Means M is the Turing machine, W is the string, right? So this is the formal definition of computability. Means computability, in case of computability, simply you require two things. One first is the machine, another one is the string. Or if we talk about the present scenario, so in this case we can say we require a machine or the computer, another one is or the program, or another one is the data set. So on the basis of data set, we can compute whether it has the better accuracy or it has the worst accuracy, right? So these are the standard two basic definition about the complexity and the computability. And the complexity class is a collection of problems which can be solved by some computational model. So that means if we want to solve a particular problem, then we require a computational model. That may be Turing machine, that may be push down automata, that may be finite automata. So now complexity class, P class is what? So P class means the polynomial class, right? So complexity class P is defined to be the set of problems solved by a Turing machine in polynomial time. So that means if we have any problem and that problem is passed to the Turing machine, and Turing machine can solve, Turing machine can produce the answer in a polynomial time. That means feasible time means after 1 hour, after 2 hour, that time is the polynomial time or the feasible time. You will get the answer. So this type of problems are called, this type of class is called class P. And this complexity class P is decidable. And these are various examples that you already read in DA. These are the example of postman problem, searching shortest path, searching a matching in a graph. All these problems are decidable. And these problems are under the category of complexity class P. So if you have any doubt, any confusion, then please let me know. So these are the basic definition about the complexity, about the computation or computability, and about the recursive and recursive enumerable. In the next lecture, we will discuss the time complexity and the space complexity. And now our syllabus is completely finished. So, for the from the next week on Monday onwards, we will start the revision. So just revise your syllabus thoroughly, completely. We will discuss all the points where you are lacking. So thank you for attending the class. Thank you.